Okay, let's do this problem using the method of sections. As I said in the previous video, the method of section is very useful when you are interested in finding the force in only one bar, two bars, a very little number of bars. No, when you want to find all the bars, this is not the method to go. So this is the case here. Determine the forces in members AF and EJ, AF and EJ. So AF is this one here, EJ is this one here. Okay, so the first question is, okay, how are we going to cut this truss in order to find those bars? Remember, we said that you must cut the truss in a way that you cut the bars that you are interested, the ones that you want to find. And of course, you were going to cut some other bars in order to have two separate pieces. You have to cut the truss in a way that you can separate the two pieces from of the truss. You have to break it in two. So you have to break enough parts in order to break it in two. So you have two independent bodies, two pieces of the truss independent from each other that you can analyze as a free body that should be in equilibrium under the forces on all the bars that you cut. The first temptation here will be to cut the truss like this. Let me draw how the truss will be if you cut it like this. So this will be the truss if you cut it along that red line. So you will have all these unknowns here. You will have this force, 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 and this force. We'll have to put the names of all those forces, like this one. This one will be, this one right here will be force AF, one of our unknowns, AF, and this one right here will be FEJ. That's the other unknown. So we have our two unknowns here, FAF and FEJ. So that's a way to cut it. Now, as we mentioned also in the previous video, you should find a way to set up some equilibrium equations that allow you to find your unknowns. In this case, we have too many unknowns. We have many unknowns. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. And the reactions, right? We have two reactions here. This one would be, maybe we can call this AX, and we have this AY. We can find those reactions AX and AY by solving the equilibrium of the whole structure. So we can consider that AX and AY are not unknowns when we go to the sections method to find the bars. So now, can you find an equation that can give us some way to find these unknowns? It looks very difficult. It looks very difficult. If you set up moments, say around point G, you can eliminate these three unknowns, but then you still have 1, 2, 3, 4, 5 unknowns. So that doesn't look like a good way to cut the truss. Another temptation will be to cut the truss, say to find the forcing element AF in this one right here. We could think of cutting like this. That will be another way to cut it. In this way, we have the joint A here, and then the rest of the structure down here with some forces, right? This is not a good idea because what you are doing here is just using the joint methods. If you cut like this, you are isolating joint A. So you are coming back to the method of joints. You will have joint A, this bar, you cut it, this bar, you cut it, and this bar, you cut it, and you will have three forces, force AB, force AG, and force AF. So that's just method of joins. And you know that in the method of joins, oh, and also I have the reactions here, right? I will have AX and AY. As I said before, we can find AX and AY using the equilibrium of the whole truss. So we can consider that we already know AX and AY. So we have three unknowns, and and with one joint you can only find two unknowns. So this way you cannot find the force that you need. So this is not a good way to go. So the way to do this, let me get rid of this here. The way to cut this in a better way so we can find a joint or a point in this truss where you can set up an equation where you eliminate a lot of the unknowns that you generate when you make the cut, will be this cut like this. If you cut like that, then the truss will look like this. And then the forces that we generate are this one, this one, this one, this one, this one, and this one. We got 1, 2, 3, 4, 5, 6 bars. So we have 1, 2, 3, 4, 5, 6 bars, where this one will be F, A, F, this one will be F, A, G, this one will be F, G, H, this one will be F, H, I, this one will be F, I, J, and this one will be F, E, J. So those are these and these are the bars that we want to find. So if we cut like this, we can set up, and let me write down the reaction. So we have a reaction here, AX and AY. And if we take moments about point F, you eliminate all these unknowns, FAJ, FGH, FHI, and FIJ. You eliminate all those unknowns because all those forces go through the point F. So they don't produce moment with respect to F. And we also eliminate AY, and we also eliminate this one, FAF. So we have an equation as a function of FEJ and AX. If we solve AX previously by using equilibrium the whole truss, we can find in this equation the force EJ. So that looks to me that that's the way to go. The same way, if we do moments around point J, then we eliminate all the same horizontal forces here, and we also eliminate FEJ, and we have an equation as a function of FAF, AX, and AY. Again, we can find AX and AY previously using equilibrium of the whole truss, so we can find AF with just one equation. So that's the way we're going to proceed. So first we said we need to find the external reactions using the equilibrium equations of the whole truss. So let's do that. Let's do the free body diagram of the whole truss. This is the free body diagram of the whole truss. We have all the dimensions. The truss is completely isolated from the rest of the world. We just need to put here the reactions, external reactions. We have here in point A, we have one horizontal reaction, let's call it AX, and a vertical reaction, let's call it AY, and there is a roller support here in joint K, so we have a Let's call it reaction at K. We know that it's horizontal. And since we don't know, they are announced for now, well, I just put them in any direction I want. They are announced. If I get a minus sign, then I know that it's going in the other direction. So and we replace the forces with known value by the value. And that's our free body diagram of the whole truss. Setting up the equations of equilibrium of the whole truss. So we have here the free body diagram of the whole truss. Summation of moments about point K equals to 0, positive in this direction, in order to find AX. So we will do here AX times 4, actually 8. Positive is going clockwise, and then this force is also positive, plus 1.2 kilonewtons times this distance, 6 meters. Now this force here also clockwise, so plus 1.2 multiplied by this distance, 3 times 4, 12 times 12. And there is no more forces that apply moment with respect to point A. This one doesn't produce moment with respect to K, because the force goes through the point, right? And so only AX and the two forces of 1.2 kilonewtons. So this equation, it has to be equal to 0. So from here I get that AX equals to minus 1/8 of minus 1.2 times 18. So AX equals 2.7, negative 2.7 equals negative 2.7 kilonewtons. Negative means that my assumption that the AX was going to the right is wrong. So this is not going to the right. This is not going to the right. This is going to the left. All right, now a summation of forces in the x direction. Summation of forces in the x direction can give me AX. I'm sorry, the reaction at K. Summation of forces in the x direction equals to 0. I'm going to do positive this way. So I have RK plus AX, but I will do something like this, right? Minus 2.7. AX originally was going to the right, so that's why I put this plus sign here. But then when I put the force going to the right, in order to put this plus sign here, with that assumption, the force is minus 2.7. So that's why I put a minus sign there. Or I can write this RK, and I can erase the force going to the left and put it going to the left, like the way it really is. So I have AX going to the left, which is negative with my sign convention. So that's, I would write something like this. So either way is the same, equals to 0, equals to 0. So RK equals to 2.7. Okay, so we have AX and RK. Now we need to find AY. We can do AY by a simple summation of forces in the Y direction. Summation of forces in the Y direction equals to 0. I'm going to do positive going up. So I have AY minus 1.2 minus 1.2 equals to 0. So AY equals to minus Oh, this goes to the other side of the equation with a plus 2.4. So plus means that my assumption that it was going up is correct, so I don't need to make any changes there. So I have all the forces. Okay, so now we can come back to our CAD here in order to solve for the bars that we need. Let me do some cleanup here. Let's put the results here on the free body diagram. So this one is going up. AY equals 2.4. AX is 2.7. AX 2.7 and RK 2.7. Actually, we really don't need RK because in the diagram that we are going to use up here in this diagram, we don't need RK. We just need AX and AY, but that's okay. Okay, this is our free body diagram of the section that we are going to use. So this is our section with the reactions right there. So we just have to set up the equations that I mentioned before. We can do summation of moments around point F. Summation of moments around point F equal to 0. And I'm going to do positive in this direction. All these forces go through the point F, so they don't produce moment. This also goes through point F, and this one also goes through point F. So the only forces that produce moment with respect to point F are AX and FEJ. So we have then FEJ times the whole distance from here to here, 12 meters, minus, because AX makes moment counterclockwise. According to my convention, here is positive clockwise, so counterclockwise will be negative, will be 2.7 kilonewtons times this distance is 4 meters. No more forces, equal to 0. So FEJ equals to, goes positive, 2.7 kilonewtons times 4 meters divided by 12 meters. So this is equal to 0.9. 0.9 kilonewtons. I got a positive, so this is tension. Because I assume in tension, so I got positive, so this is tension. So this one is equal to 0.9 kilonewtons. Now we do summation of moments about point J. This one here. Summation of moments about point J equals to 0. I'm gonna do positive in this direction. So I have the positive for the force FAF. So again, all these forces go through point J, so they don't produce any moment. FEJ doesn't produce moment because it goes through the point J. So then the only forces that survive are these three forces. So then we have FAF times all this distance, 12 meters, minus AY, which is 2.4 kilonewtons, times the same distance, 12, plus AX. Force AX produces positive moment, right? Produces around point J, produces a moment in this direction, right? Which is positive, considering my sun convention here. So that will be positive 2.7 kilonewtons times this distance 4 meters equals to 0. So then we have F equals to 1 over 12 meters multiplied by, this goes positive, 2.4 times 12, 28.8 positive, 28.8 positive, and then negative 2.4 times 2.7 times 4, 10.8, and this is kilonewtons meters. So this is 18 divided by 12, 1.5. I get a positive 1.5 kilonewtons, so I get a tension again. And that's the solution of the problem. You will write very nicely here, FEJ equals 0.9 kilonewtons tension, and FAF 1.5 kilonewtons tension. You could have used the lower part, same thing. You would use the reaction at the bottom joint F, but it will be very similar. You take those specific points where you eliminate the moment produced by all those unknowns that you don't care. So that's the trick with the sections method. You have to make a cut in a way that the forces that you generate can be eliminated by finding the appropriate joint, or the appropriate point. It doesn't have to be a joint. You can find any point in the universe in order to eliminate forces that you don't need. So the ones that you want to find survive in your equation, and you try to make your equations as simple as possible. All right.